right. So I mean, I went through and did the answers. I'll write them neatly so you can actually read them and post them online. And then I'll give these back Monday. I looked through quickly. Okay. I did something cheeky. So question 6 was, what did Einstein get his Nobel Prize for? Question 7 was, what is the photoelectric effect? So the answer was the photoelectric effect. So it's actually very, very common, even like PhD scientists, to think he got it for relativity, which a lot of you answered. E equals mc squared, relativity. He never got the prize for relativity. Yeah, so someone put quantum mechanics, and that is actually reasonably accurate. The photoelectric effect is the origin of quantum mechanics and how we knew classical didn't work. Okay, but we'll do that later. And just for your interest, Shockley-Queisser limit is the maximum efficiency of a solar cell, which we'll look at a little bit briefly later too. I just like the name Shockley-Queisser. It's fun. Otherwise, I mean, I think the stuff we actually covered, people did generally well. And then, of course, I did not give you the equation for a cross product in an exam. I would, because it'll be nicer than that. But I wanted to see how you did. Okay, so this was a bit challenging. But generally, yeah. The stuff we've covered, I think I'm happy with. You learned. That's good. So we'll push ahead. Okay, so in the notes, this question is in the notes. And I'll just solve it here. So it said that we have a capacitor. So let's try it. Okay. It says that the space between the two metal plates is 2 microns. Okay. So I keep doing this, giving you annoying units. There's a general thing. If you make everything in kilograms and meters and seconds and coulombs, the answer will just work out correctly. So we always just have to convert these to the meters or the kilograms or whatever. And like the first question that I gave you cubic meters, but then I gave you the density in liters, not cubic meters. So you had to convert. Okay. What else do I say? I say that the area of the plates is a square centimeter, not per, square centimeter, okay? And then it says ER is, what was it, 2.6. So that is, oh, and then it also says that the capacitor is charged with a voltage of 3.0 volts. So I'll write delta V is 3.0 volts. Okay, so let's quickly review charge, voltage, capacitance, and energy. So charge, coulombs. So this will be units, and this will be charge. For batteries, instead of saying charge, people like to write capacitance. No, capacity, sorry. See, I can't even do it. It's a mess. Okay. So for a battery, they'll say capacity. What they really mean is it's a charge. You can think of it as a number of electrons. You can think of it as a bunch of coulombs, whatever. Okay. People will also write amp hours. Okay. Well, let's do current. which is coulombs per second, or if you prefer, those are the same thing. So remember, going from watt hours to joules, there's a factor of 3,600 because there's 3,600 seconds in an hour. It's going to be the same going from coulombs to amp hours. So to get an amp hour, we need 3,600 coulombs. 1 amp hour, which is coulombs per second, is 3.6 times 10 to the 3. You can also write it this way, coulombs. It's all the same. That's a 10. I did very poorly in printing as a child. Couldn't stay between the lines. You know when you're like 6 and they make you write between the lines? Mine was all over. Anyway, it has not improved. So I'll try to be neat for you guys. Okay. So we have charge, we have current. So the difference is just time. So this is the same as energy and power, okay? Energy, we did joules. Well, E sometimes, we'll call it EE for electrical. We can also write UE depending on the context. Actually, I think I write U in the notes, don't I? So let's do this. U, so that's joules. Power. Watts, which is just a joule per second. Oh, and someone had asked, why is it I'm always using superscripts? So if you decide in your engineering career to get into modeling, so if you're using MATLAB or ANSYS or whatever, the coding always uses superscripts like this, and it becomes much easier for that. I had to think about it. Why do I do it that way? But if you prefer to write it as fractions, totally the same. Okay. There's no difference. Okay. Charge, current, energy, power, voltage. So a voltage is always a difference from two different points, okay? So if you're taking electrochemistry now, or if you took it before, you might have heard potential. So the voltage is the difference between two potentials. So that's just sort of a language thing. I'll just use the delta V in general to show that I mean voltage, and that will help because the unit is volt, which is also a V. That's why I'm trying to do that. Hopefully then it's easy to keep track. And occasionally V is volume. Oh well. Okay, so it's volts. That has units of joules per coulomb. And then finally, capacitance. C, which is units of farads, which is coulombs per volt. Okay, so we can come back and answer this now. So what I'm saying with capacitance is, although I've said how to calculate it for this plate, I didn't really define what on earth it is. Probably would have made sense. So in general, capacitance is charge divided by the voltage. Okay. So the question asks you, how much energy is this going to store? It doesn't ask you for charge. Okay. Oh, so we know C is ER E naught A over D. I didn't tell you epsilon naught. Coulombs squared has weird units, unfortunately. Per kilogram. So again, if you want to put that as a denominator, that's fine. Per cubic meter, then second is positive, square seconds. Okay. I chose these units because they'll be a little better for what we're doing. If you look it up on Wikipedia, it gives you a ton of different ways of writing the exact same value. Okay. So we know the voltage, we can calculate the capacitance, we have everything we need. And so what this equation is actually going to tell us is the charge. So we can calculate the charge that we have here, but that's not the energy. So if I finish all these things I'm trying to show you, I'll say this is a very useful thing. So the voltage is telling us how much energy there is for the amount of charge. So to walk through, we know the design and we've applied a voltage. So we can figure out how much charge there will be. We'll just move this over there. And then from that charge, because we have the voltage, we can figure out the energy. Does that make sense? Hopefully. So then the actual solving of it all, you could do it in steps. You could do one step at a time, or you could try to do it all at once. It's up to you. Some find one much simpler, the others find the other much simpler. It's all about whatever you make the fewest mistakes doing, okay? So if I was to plug in all these numbers, I think in the interest of time, I will just show you the answer. So you get these weird units, -1, okay? So the only difference between these units and this is that I've changed the meters a little bit. Oh, and when you do this, what I recommend is just convert these to meters. Okay, so there's 1,000,000 micrometers in a meter. Wait a minute, no, because I wrote the question wrong. The gap is 20 micrometers, sorry. That makes more sense. And this is so there's 100 centimeters in a meter. That means there's 10,000 square centimeters in a square meter. And in the quiz earlier, there's 1,000,000 milliliters in a cubic meter. Or 1,000 liters in a cubic meter. Anyway, you can boil it back down to there's 100 and just square it. So again, try to practice being comfortable going between units. Okay, so this is C. So then I can go to my C, Q equals C delta V. I might have to erase that in a second. Yeah, I think I shouldn't write this low. You all have that copied? I'll just write it right here. Okay. Rather than crawling on the floor. Okay. So Q, from our definition of capacitance, Q is going to be capacitance times the applied voltage. So I mean, I've powered this up with a battery or plugged it into some device, right? I've given the electricity. We won't worry about how I did that. Well, you can convince yourselves. So by the way, actually, this weird looking thing will simplify to coulombs per volt, or why don't I show you that actually? Hold on. So you had square coulombs, square second, kilogram, square meters. So a kilogram square meter per square second is a joule. So that's actually what this bizarre unit is. It's square coulombs per joule. And a joule per coulomb is a volt, so you could write coulombs per volt. And they all just interchange. Okay? So I'll just write the answer. It's just this times 3. Minus 10 to the minus 10. So please, there we go. Now we have a nice unit. We can say the amount of potential energy we've stored is Q delta V. So we take this, we multiply it by volts again. And you'll get 1.0 or so. I believe we're down to nanojoules for this little thing. That's not much energy. But that makes sense. A little capacitor like this, it does store energy, but not much. Okay? All right. So please, when you're reviewing your notes, try to do the calculation. Email me if I made a mistake. I'm sure the equations are generally right. I do not guarantee I didn't type it in wrong. I'm pretty sure this is right. Okay. But make sure you're comfortable doing it. Practice with the units. I know it's a bit messy and weird, but it's an extremely useful skill to be able to switch between units. And when you realize this works out to coulombs very cleanly, you know you did it right. And you feel like, yeah. Whereas if it works out and it's got the wrong unit, you did something wrong. Okay? So it kind of builds in a self-check when you're doing these questions. Okay. So that's not the end of my notes. They're just in a weird order. So that's the end of those notes. So we're going to move on to the next sort of unit. Are there any questions before I move on? All right. You'll be happy to know there's far less math in the next, and less equations in the next section. Although I think I'm starting with some trigonometry. But the next section is going to involve a lot more thinking in 2 and 3 dimensions, okay? Because we're going to actually look at the structure of materials at an atom level, and then eventually use that to understand about properties and things, okay? All right. And all of this math we did this week will make reappearances throughout the semester. So, okay. This is good. So we've learned how to store energy with gravity. We've learned how to store energy in a capacitor and how to calculate that energy. The pumped hydro was on the order of thousands of megawatt hours. This is on the order of nanojoules. So we are way all over the spectrum here. And everything else will be somewhere in the middle. unless we do nuclear, which is, I don't know, if you saw Oppenheimer, or there's a really nice heavy water war thing on NRK. No? Okay. Oppenheimer, I found, was very long and a little slow. I thought it could have been a bit shorter. I also felt like I should have been more interested given my job, but maybe that was the issue. Okay, I don't know. You weren't Barbenheimer fans? No? Okay. Yeah, okay, good, you are. I was gonna say. All right, so we're gonna talk about lattices. And you may have heard of a lattice as like a grid that you use to grow peas and beans on, which generally speaking, a lattice is just a pattern that repeats itself in many directions, okay? Well, what does that have to do with materials? So when you learn chemistry, you probably learn things like CO2. I don't know why I'm drawing it like that. You know, you might have learned like molecules, right? Or hydrogen. You know, and they make you draw electrons. You don't have to do this. It's not the point of this course. So that's all molecular chemistry. And that's usually how we learn, is going from atoms to molecules with 2 atoms, and then we go to maybe 3, like linear CO2, or H2O is bent. We learn that way, right? But for solids, we don't have this. You end up with this network that goes on for trillions of atoms. So we can't think in terms of these really simple things, okay? Although a lot of the theory ends up being the same in ways, but the way we approach it's going to be different. So we're going to start with the geometry. We're not going to worry too much about the orbitals and anything like that. We're going to take metal, any metal, okay? So the composition, I think I showed titanium later. I think is one of the examples I have loaded. So titanium, it's a metal, okay? It's transition metal. So its chemical composition is very simple. So what's its structure? Well, it's not a gas, it's not just an atom by itself. It has an actual chemical structure, but it goes off. So what we do is we treat titanium, treat atoms as spheres, okay? We say, okay, so what it's going to do is it's just going to jam itself in and fill as much space and squeeze together as closely as it can. That's the simplest way of arranging spheres. Well, let's start with circles and 2-dimensional lattices, and then let's go back to the spheres and let's have a look at titanium, and I'll even show you in 3D. Well, we'll see how far we get. Okay, so if I have titanium, I can put more titanium, put it in a nice row. Where's the next row going to go? Is it going to sit right above? And we will see there are metals and there are materials that do that. It's not a very efficient way of filling this space. You're going to have but imagine they're good circles, okay? There's a lot of empty space, okay? Let's figure out how much space there is. So this is an example of a 2-dimensional unit cell. What the heck is that? So a unit cell is something that if you move it over and up in the various directions, it repeats itself. So if I take this and put it there, you get the exact same thing back. And again and again. And if I move it up, you get the same thing back. And again and again. So we like to position the unit cell on the center of atoms because it's easier. You could put your unit cell in the middle of the empty space. It would still work from a math perspective, but from a practical perspective, it would be annoying, okay? But like, you know, if I wanted, I could actually, there's old German texts that do this. I could say my unit cell has this titanium right in the middle. Yeah, the math ends up being more annoying later on, but there's nothing wrong with this. These unit cells are equivalent, okay? So when I take the unit cell and I repeat it, that's the lattice. That's that repeating two-dimensional structure. And we'll go to three dimensions later. So this would be a very simple square unit cell. I'm going to say D is the length. The angle is 90 degrees. So the question is, how much of this space is filled by atoms? Okay, so let's call it the packing, that's a K, factor, and it's going to be the area of the atoms, which I said was titanium, although this isn't how titanium works. Let's just put atom. Atom does not start with a D. Atom over area of the cell, okay? So what's the area of the atom? They're all the same. Anyone? Area of a circle? You've answered already. Someone else answered. Someone must know the area of a circle. It's not a trick question.
Pi r squared?
Yes, thank you. Oh, I was getting worried. Okay, so it's pi r squared. I've given you the unit cell parameter d, which is 2r. That's the diameter. So the area of the atom is going to be pi over 4 d squared, where d is just 2r. So it works out. Wait, yes. And the area of the cell.
D over 2?
So the cell is the whole square. No, it's not d over 2.
D times D.
Yeah, d squared.
No, I meant with the atom.
Pi r squared is equal to pi over 4 d squared.
Isn't R D over 2?
No, so it's d equals r over 2, d squared wait, that's wrong. 2r. It's right in my mind. There we go. This is actually a very practical thing in engineering. Like mechanical engineers will often exclusively use the area as d squared over 4 because measuring the diameter is very easy. Measuring the radius is silly. And so, but they're completely equivalent. Yeah. So just make sure though, the square has to apply to the 2. That's why. Okay. Right, so pi by 4, I don't know what that is. Someone can calculate what pi divided by 4 is. It's going to be like 72% or something.
78.
Oh.
0.78.
I went the wrong direction on that one. All right. So let me show you another way of packing the circles. Okay. So I'll have to look up. I believe gold packs this way. Okay. where it's the circles are right on top in a very square arrangement. I'll have to double check that's true. Okay, and we'll see what that looks like in 3D in a minute. Titanium does not. So titanium, it sort of rolls in, okay? And you can kind of guess these spaces look smaller than those, not just because I drew it terribly. All right, so this is my 2D unit cell for what we call close packed circles. This is going to be the most efficient possible way to fill a space with circles. So let's say the unit cell parameter is D again. I'll call this theta. Sorry, that's bad. Okay. Theta is going to be 120 degrees. You could also define it as this one is 60 degrees. That's fine. Yeah, well, crystallographers like to use the larger angle. They're equivalent. So we're going to do the same thing. Packing factor is the A atom over the area of the cell. Okay. Yeah, well, 60 degrees. I'll use degrees. Crystallography often does. If you prefer radians, pi by 3. Okay. So if you don't remember your SOHCAHTOA, I assume that's how you learn it here. What we're going to need to do is find the size of the height of our unit cell. Okay, so this is just, I've redrawn this thing. As you can see, if I move it over, I get the same thing. If I move it this direction, I get the same thing. Okay, so that's our unit cell. It's slanted now. It's not a square, but that's fine. Unit cells don't need to be square. And they frequently are not square. So they're not your X, Y, Z Cartesian coordinates. Again, when we get to 3D. Okay, so the area of the cell is D times H. A equals D times H. And H so sine 60 is opposite over hypotenuse. So sine 60 degrees okay. It's height. You're right. The hypotenuse is D, not H. That's annoying, isn't it? There. Let's do that. I hadn't thought of it that way. Yeah. All right. And you can convince yourselves that Sine 60 is root 3 by 2. Sine 60 degrees is square root of 3 over 2. Which you probably had memorized once many years ago. Okay. So the packing factor, if we go back to this, keep that separate. We have on the top pi over 4 d squared, and on the bottom, so if we do d times root 3 over 2 and then multiply it by d because it's the area, we have root 3 by 2 d squared. Which is pi over 2 root 3 90. Okay. So again, try to go through that math, make sure you're comfortable area of, the rhombus. You would of course have a calculator, so if you need to calculate sine pi by 3, you could do it analytically and get the number. I think I might give you some of the main ones actually, if that was important on a question. Like sine, you know. Yeah, I think I would. The point of the class isn't to make you memorize trigonometry tables. Okay. What I want you to understand, like, what am I doing here? What is the lattice? And what does this represent? So this means that when we have a material, some of it's just empty space, right? It's a vacuum inside of a material. So no matter how much you push on something, there's always going to be empty space. But you see there, we have more empty space, and here we have less. So that means a lot of materials want to do this close packing that we call it, all right? In order to go to that structure, there would have to be some sort of chemical reason. You know, orbitals are saying we'd rather be this direction, and they'd have to overcome. There's going to be some sort of an energy penalty to be in that less ideal structure, because vacuums don't like to exist. We know that. Okay. And that's time. So we'll start with three-dimensional on Monday. Okay. Again, as always, please, if you have questions or anything, email. If you have concerns or things you'd like me to go over again. Otherwise, go through those notes. There's a couple questions we didn't do in class. Try to be comfortable, go over the ones we did a few times. Yeah, and as I say, so sometime in the next few days, I'll try to post some resources that'll help moving forward. One example, there's going to be a software for looking at crystal structures that I would recommend you install. I'll show you how to use it probably Monday. Definitely Monday. Yeah. But I'll post where it is and how to put it in. And it works on Apple or Windows. And if you have Linux, you're on your own. Okay. All right.